This is the sixth talk about basic electronics. The purpose of this talk is to explain a few concepts about impedance relevant to the neurophysiology board examination. This talk will be conducted in a question and answer format. Here goes the first question. The symbol for impedance is A, L, B, I, C, R, D, Z. The C is not only for sorrow, it is also used for impedance. So the answer to this question is D. Next question. What is the unit for impedance? A ohms, B volts, C amps, D Henry. You remember this triangle from before. It provides a way to remember the relation between electromotive force, current, and resistance as established by Ohm's law. When dealing with impedance, we only need to substitute the letter R with the letter Z. The unit for impedance is the same as the unit for resistance. It is the ohm. So the answer to this question is A. Next question. The factors involved in impedance are A. Resistance, B. Capacitance reactance, C. Inductive reactance, D. All of the above. Impedance is a quality of alternating current brought about by the back and forth movement of charges in a circuit composed of resistors, capacitors, and inductors. So it includes resistance, capacitance reactance, and inductive reactance. Inductive reactance is also encountered, although to a lesser extent, in purely resistor circuits, as long as the power source is alternating current. This is so because all resistors circuit have some inductive reactance. So the answer to this question is D. Next question. The formula for capacitance reactance expresses an inverse relation between the size of the capacitor and reactance. A true, B false. The formula for capacitance reactance indicates that the larger the capacitor, the less it will resist current. So the answer to this question is A. Next question. The formula for inductance reactance expresses a direct relation between the value of the inductor and reactance. A true, B false. The formula for inductive reactance indicates that the higher the magnitude of the inductor, the more it will resist current. So the answer to this question is A. Next question. All major neurophysiology textbooks represent impedance with the same formula. A true, B false. Different formulas for impedance are presented in different books. The formula you are just looking at I find it too complicated to even take into consideration. This new one is less complicated and is present in two major textbooks used by neurophysiologists. This later formula is from Everson's book. It looks at first glance similar to the one just above, but it subtracts inductive reactance from capacitant reactance, whereas the formula in yellow subtracts capacitant reactance from inductive reactance. So the answer to this question is false. B. Next question. In a purely capacitor circuit, current and voltage are in phase. A true, B false. To answer this question, I will start in this frame by representing current as a yellow sinusoidal wave, and in subsequent frames I will superimpose to it the voltage in pure resistive, capacitor, and inductive circuits that would go along with the current I have represented in this frame. It is important to point out that the arrow in this frame points to a very important element in this figure and to our study, that is time. So in this frame I am showing the relation of alternating current and voltage in a purely resistive circuit. The green line represents voltage. As you can see, when using a simple resistor circuit, current and voltage are in phase. If, on the other hand, we look at a pure capacitor circuit and plot voltage with the same time constraint, we find that voltage represented by the aqua sinusoidal line in this frame is displaced forward. This forward displacement in time represents a delay. In this case, voltage lags 90 degrees in reference to current. Lastly, using the same conditions but now looking at a purely conductive circuit, we find that voltage represented here by the magenta sine wave leads current by 90 degrees. So the answer to this question is false. Next question. The voltage-time relation between inductive and capacitance elements in a circuit are the reason for their subtraction when calculating the impedance of a circuit. A true, B false. In this frame, I have just represented the voltage-time relation for each of the three factors involved in impedance. If we remove the sine wave representing the voltage generated by current when traveling through the resistor element, we can see that the voltage curves generated by inductance and capacitance elements in the circuit are in opposite direction. And as you can realize, they work against each other. It is for this reason that in the impedance formula they are subtracted from each other. I think the order of subtraction is dictated by the magnitude of the factors involved. The one smaller is subtracted from the one that is larger. But I may be wrong. So the answer to this question is true. Next question. For EEG, electrode impedance is measured after all electrodes are attached to the head. A true, B false. Electrode resistance is measured with the electrode not connected to the head. Electrode resistance measures electrode integrity. it is measured using direct current. And as I just mentioned, it is measured before the electrode is attached to the patient in order to see whether the electrode is or is not broken. Measurement of resistance is seldom done. Electrode impedance measures electrode scalp interface. Hence, it is obvious that it has to be tested after the electrode has been placed in the scalp. Remember that for safety reasons, you must first turn on the EEG machine prior to connecting the electrodes to the scalp, and also you have to disconnect the electrodes from the scalp prior to turning the machine off. So the answer to this question is
true. A.
Next question. Which of the following is not true regarding impedance? A. Opposition to alternating current. B. Testing requires electricity to pass from the electrodes to the scalp. C. Should be kept between 100 and 500 ohms. D. 50 Hz current is best to test EEG impedance. Electrode impedance is measured by passing a weak alternating current from the electrode selected for testing to the patient's scalp. The electricity from the EEG machine impedance meter goes in to the selective electrode, spreads in the scalp, and returns through all other electrodes connecting the patient to the EEG machine. The measured impedance mainly reflects the impedance of the selected electrode, since the return path of the electricity takes it through multiple electrodes connected to the patient. Therefore, the amount of impedance of the non-selected electrodes is negligible. The impedance of the selected electrode should be between 100 and 5,000 ohms. The American Clinical Neurophysiology Society recommends a state that the impedance less than 5,000 can be obtained regularly in pediatric patients, but higher impedance can be allowed. The recommendation in the general section of the guidelines of this society states that an impedance of 10,000 ohm is acceptable. Probably more important than the total impedance is the difference in impedance between electrodes. A difference of less than 20% between electrodes is recommended by some. The frequency of alternating current used to test impedance should be 10 Hz. This frequency should be used because you want to test the system with a frequency that corresponds to one of the frequencies that you're normally evaluating when you look at an EEG. So the answer to this question is D. Next question. The impedance of an amplifier should at least be dash times higher than the impedance of the electrode. A 5, B 1000, C 100, D 0.1. Impedance of an amplifier used in neurophysiology equipment should at least be 100 times higher than the impedance of each electrode. The modern EEG machines have very high impedance in the range of 200 million ohms. So the answer to this question is C. Next question. Very high electrode impedance results in A. 60 Hz cycle, B. Signal attenuation, C. slowing of the background, D, all of the above. In this frame, I am representing the impedance at FP1 and C3 to be 4000 ohms. Below, I am representing the waveform generated by these electrodes from an imaginary head. If instead of 4000 ohms, the impedance of both electrodes is 20,000, an EEG activity of similar value as the one we just alluded to will produce a tracing with significant lower amplitude than the amplitude generated when the impedance of both electrodes were equal. If the impedance between two electrodes is larger than 20% different, in this case both are below 10,000, but one is 9,000 and the other is 1,000, the recording from such a channel will have a significant amount of 60 Hz artifact. If the impedance of two electrodes connected to one channel is less than 100, the activity capture is likely to be the product of a salt bridge between them. So the answer to this question is B. Next question. Coupling of one electrode of high impedance with one with low impedance results in A. 60 Hz cycle, B. Signal attenuation, C. Slowing of the background, D. All of the above. Impedance mismatch renders derivation more vulnerable to 60 Hz artifact. So the answer to this question is A. Next question. Coupling of two electrodes with very low impedance. A. Results in flattening of the recorded activity. B. Indicates a salt bridge. C. Does not indicate voltage. D. All of the above. Coupling two electrodes with very low impedance results in flattening of the recorded activity. This is due to the formation of salt bridge between the electrodes. So the answer to this question is D. Next question. The only known source of 60 Hz artifact is electrical noise. A. True, B. False. 60 Hz artifact can arise from magnetic noise and from electrical noise. In case of electrical noise, it arises most of the time when there is impedance mismatched. So the answer to this question is B. Next question. Correcting electrode mismatches within 20% always eliminate 60 Hz power line artifact. A. True, B. False. Electrical noise will produce 60 Hz artifact if an electrode mismatch is present. So correcting the mismatch, as you see, is represented by the dashing of 9,000 to 4,000, will make the 60 Hz artifact disappears because electrodes are going to be matched. On the other hand, 60 Hz artifact that occurs as a consequence of magnetic noise may be present despite good electrode match, and when present will not be corrected by eliminating electrode impedance mismatched. The only way to eliminate 60 Hz artifact due to magnetic noise is to remove the source that is creating the magnetic force from the EEG area. So the answer to this question is false. Next question. Bundling and twisting the electrodes leads near the head of the patient before running them to the amplifier decreases 60 Hz artifact produced by inductance. A true, B false. When the electrodes running from the patient to the EEG machine are far apart, they are exposed to different magnitude of magnetic forces which will produce different values at the amplifier. If we bundle them together, they're going to be subject to the same magnitude of forces. And thanks to the differential amplifiers, whatever is the same will be rejected. So it is better to bundle all the electrodes wired together as close to the head as possible than to allow them to go their separate way to the EEG machine. So the answer to this question is true. Thank you.